Some more information on path info nodes. I kind of wave my hands about being a peer to dev info nodes. These are the new construct relative to the device framework with MPxIO. They tie in a matrix to the VHCI and the PHCI. They have the same unit address. It's just sometimes we have this problem in the framework where concepts that are really important tend to get their own interfaces, and that actually means that you don't see them. You don't actually. It obscures the concept. Like we have quite a few instances of this where something's so important we promote its implementation, and then you don't see it anymore in PRTconf. Okay, so it's actually, unless you know the details of what's going on under the covers, it's kind of hard to see the importance of what the architecture really is. And the path info unit addresses are a good example of that. We don't really show there's a separate path info field for unit address. PRTconf doesn't display it. So you're left with no, if you're just kind of browsing around, you don't form the connection that the unit address of a path info node is the same as the unit address of a dev info node if the device were not enumerated under MPxIO. Okay. So path info node for every physical path. The VHCI driver, is acting as a transport for the target driver. So the target driver, as Sumit showed you, it has this SCSI init packet stuff, and then SCSI start to actually send a packet down the transport. That's still happening identically within the SD driver, so within the driver here, but now it's sending a packet to the VHCI. And so, in a nutshell, the responsibility of the VHCI is to look at all the path infos that provide connectivity to that specific identity, device identity, select one of them based on either which one is the primary in a asymmetric, which one is the one you're currently using, the other ones are all failover paths. Or in the case of a symmetric, you have a bunch of paths to choose, which algorithmically is the most optimal to choose. Choose that path, clone the SCSI packet, and send it to the PHCI. So it's kind of just a multiplexer. The VHCI is a multiplexer between SCSI packets coming from the target driver and directing them to specific PHCIs, then waiting for them to complete, matching up the PHCI completion back to the initial one to the target driver, and then completing back to the target driver. So, conceptually, that's a pretty, not too hard to grok, I think. It's just kind of a conduit for SCSI packets. So this is showing, unit addresses and so forth on paths to the same device. And in this case, they got it right, 21 and 22. So it wasn't 20 and 21. It was 21 and 22. Different port address shown, whereas the diagram that I said had an error on it a couple back had that wrong. So we have a fairly basic state model for paths. And, the thing to keep in mind here, we talked a little bit about the state model for dev info nodes. That was the DS proto to bound to, proto to linked to bound to initialized to probed to attached to ready. Okay, most of the state model for device access is actually associated with the dev info node. The path states are really much more, is it online? Is it something that I can actually use? Or is it sitting there in standby waiting for a failure, or has it already failed? Okay, so there's actually tie-in to the simpler path info state model directly from some of the configuration operations for PHCI's devinfo transitions. Okay, so any questions on state stuff? I believe all the utilities, empath ADM and PRTconf, all show path state.
Default and online. There's just no description for those. Those are actually separate states. I think I had gotten a comment on that once. Somebody asked me about it.
Okay.
Yeah. So it's not init online as a state. It's init and online are separate.
Right. So init is during the creation of a path info. Fault is that it's faulted. Offline is that it's been manually told not to use. The typical states are online and standby. Standby is only used in asymmetric environments where only one, in an asymmetric environment, only one path can be online.
So there's 5 states.
Yep.
Yeah.
1, 2, 3, 4.
Right. It looks like there's 3. How
Right,
is it
right.
like-
Yep.
Yeah, that's
Right.
a little
Okay.
deceptive. Load balancing is a concept that applies to symmetric device access, where you have a choice of online paths, and which one do you choose? And we have a number of different algorithms that are used, that you can set through empath ADM or that are default as defined by a specific failover ops. And I'm sure Wayne could tell you too about how TPGS, I think, also allows description in a standard way of the device telling you how to do this, what load balancing to use.
Load balancing as it is which
Online,
paths
offline paths,
and
or
states.
symmetric, asymmetric.
Right.
Okay.
Right. And you can actually just, maybe a clarification for asymmetric, you could actually have multiple paths online for an asymmetric device. It doesn't have to be just one path,
Okay.
just a minor.
So the multiple paths, but only one group is online.
Correct.
Okay. That comes to the, Hyun was talking about something called TPGS, which is transport group, target port group select.
Right.
And it's not just one, there can be multiple target ports within a port group.
It's just that each group has the identical behavior as far as path states and transitions.
Our hope is that going forward, more and more devices will actually adhere to the TPGS ANSI standard. It's a T10 standard now. The reason for that is that then things are auto-configuring. We have support for TPGS. It's the highest precedent choice among our various plugins, and as new devices come out that actually adhere to the standard, we don't have to release patches or anything in order to get them to enumerate correctly under MPxIO. Failover is, when a path goes bad. In asymmetric, you're actually switching over to standby paths. In symmetric, you're just marking, no longer going to use a failed path, so it diminishes the potential bandwidth. And as long as it's not the last path going away, you still have transparency relative to any application that has the device open. Driver loading, we actually talked about this to some extent earlier in regard to, again, back to the dev-info state model. Between the states DS initialized and DS probed is the first time the driver is actually loaded. VHCI is sort of a special case in that the core framework code kind of at the same time it creates the root of the dev info tree, it also creates the VHCI node. That's so that it's there for as a registered VHCI. In newer code, so we have a path, in the same way we have a path to inst file that you probably are all familiar with. There's the use of that file helps identify if all you do have is a McNod, it helps identify which stick to a device you actually need to use to resolve that path. So in a very similar way, we talked about how file system stuff can actually reach into a Nexus driver to initiate creation of new namespace below it. And that's exactly what happens in the VHCI now. The VHCI actually, when you have a dev path going in here referring to a device by its identity, there's actually a path, a hidden file that's maintained that is from dev ID to all paths that registered that dev ID, okay? And the VHCI code uses that to drive attach of the specific. So if you're asking for a specific identity device to be opened and you don't already have paths to it, there's actually a file that maintains a cache of which sticks within the device tree to attach in order to instantiate those paths. So, we don't wait for every PHCI device to attach before letting device access actually proceed. In fact, as soon as there's one path that's instantiated, the open, from an extension of the file system into the Nexus driver, the node's created and the code is off running and starting to send real IOs. And then additional paths are like coming on asynchronously, driven by a different thread within the VHCI Nexus. That's code that Ramaswamy implemented. Device enumeration. I just talked kind of about how that is on demand with a cache to actually take a VHCI path into the Nexus for what you would see is the DevFS file system at this level saying, I need to find a child called this. And it looks at its children over here and says, well, I don't have a child called that. Okay, so the file system actually drives a bus config operation into the Nexus driver and asking the parent Nexus driver, in this case VHCI, can you discover something called this? Okay, and in the case of the VHCI code, that's where that cache comes into play. It says, well, I know that last time I booted, this device identity has all these paths, meaning PHCI paths. And so it will drive attaches to those specific sticks, those specific paths through the namespace here, again through DevFS, coming down, and here you might be attaching PHCIs that weren't attached before, as a result of this operation extending from the file system into the Nexus, saying, okay, these are the paths I knew before. Well, those don't exist either. So go attach, this driver, attach its children. So, things are really extremely dynamic now. And the benefit of all this dynamic stuff is really, if you were ever in support for like 7 or 8, DR was just a nightmare. It was numerous problems, even continuing into 9. And, now with everything being so dynamic, actually, we're doing DR type operations all the time. We are dynamically attaching needed devices and keeping, particularly on debug kernels, keeping what is actually currently instantiated to a bare minimum, so that as devices are referenced again, we're once again testing all the DR code paths and locking and so forth. So, we've had, very little problem with DR since S10. Now that we have a real architecture with real locking and exercising it, instead of being the 0.001% operation, which brings down the whole machine, it's getting used much more frequently now, and the reliability has gone up. That's not to say there aren't some areas, like we still have some issues in power management in particular, where we could use some more reliable coding practices. So, this is describing sort of what I said. There's a cache that drives attach of the PHCIs, and then what happens when you actually get to an NDI, MDI capable Nexus that's actually servicing these bus config operations is actually quite complex in itself. The assumption for drivers like this is that a given device actually can be enumerated under MPxIO. So it actually forms up the child node, like the SD node, under VHCI, and then tries to initialize that through the MDI interfaces. And that may not work. The VHCI driver actually, when it sees an initialization operation, it has each client actually has to be accepted by a specific failover operation, okay? And within the kernel, there are essentially separate modules for LSI versus Sun T3s versus EMC versus TPGS support. And there's a hierarchy of calling these modules and saying, is this a device you're willing to support? And pretty much that answer is based on is based on inquiry data and device identity data. As a top level thing, you better have a GUID, because that's what our whole namespace is made of. The TPGS failover plugin looks at the standard inquiry data saying, do you support TPGS? Other plugins actually have vid-pid tables that we are constantly, having to update, particularly the LSI ones, as new products come out, in order to have a failover module that actually accepts the device. In terms of device acceptance, before getting to the failover modules, and the probing of asking each failover module, is this something you're interested in? There actually is an override, a SCSIVHCI.conf override mechanism, which is also vid-pid based. And that override mechanism also allows you to say, on a per vid-pid basis, don't enumerate this device under MPxIO, or vector it to a specific failover module. So, with that we can, if for instance a customer had some third-party product and he wanted to use MPxIO for some things, but not for this Hitachi, because Hitachi was insisting on their own failover stuff. You could actually, edit the vidpid table in SCSI-VHCI.conf and say, I don't want you to enumerate this. Or if there's a new LSI thing that comes out in the field and we haven't gotten our patch out yet to the vidpid table compiled into the failover module, then you can edit the table and add it specifying a specific failover module as well. Right. So that's the LSI table, or no? It's the fully symmetric. Okay. So we can disable, or we can, go to fully symmetric. At least those are the only ones that are documented. We're actually in the process, like hopefully in days now, going to be putting back some stuff to expose MPxIO to the open Solaris community. Currently, all of the SCSI VHCI code is actually over enclosed, and all of these failover operations, implementations that I'm talking about that are vendor specific or symmetric, asymmetric, LSI, EMC, those are actually sort of architected as separate modules, but implemented as part of a monolithic SCSI-VHCI.conf. And some of those actually do contain encumbered code. Like the EMC failover module contains some information which for some reason EMC considers proprietary. The same thing with LSI. So what we're doing in regard to getting this to the open Solaris community is breaking each of those failover operations into a separate module that can then be dynamically loaded by the SCSI VHCI code itself. And that lets us move the core SCSI VHCI code plus all the public either TPGS or Sun-specific failover modules for like T3 and so forth that we've implemented and we own the rights to. We can move all of that into open so that now developers can actually see all the guts plus example failover implementations without incurring the without exposing the encumbered EMC and LSI components. So actually, when that occurs, if you do a mod info or something, I actually have that up on a. So typically, before you would have seen a single kernel module for SCSI VHCI, and now you see actually separate modules, and they're also renamed to be more indicative of what they're actually doing. This is the standard symmetric module. This is the T10 standard TPGS supported one. Asymmetric for Sun is also in public since we owned that, and those two asymmetric ones are encumbered. So the hope is with there's not a lot of change in the actual functionality. It's just a change in the way that the plumbing of the modules occurs, so that we can get as much of the source as possible to the open source community. And so basically everything goes open source but these three modules. And this is the real important one. That's the core module. So Ramaswamy's slides are calling out where these cache files actually exist within the file system. For if you're in the VHCI implementing a bus config operation asked to find paths to a given device identity. How do you find the physical paths that last represented it? If you, the next slides, so you can understand how that works when they're there. When a given path is actually not there, then we actually have to do a much more complete and more time-consuming discovery to try to find some driver that registers a dev ID with the appropriate identity in order to be discovered under VHCI. This slide is the 99.999% operation slide. You know, it's been a long time talking about auto configuration stuff, which I think is really important and useful to have some grasp of. This is a slide that talks about, okay, you're actually doing I/O. I went through this to some extent, talking about how, you can look at the slide for detail, but basically the target driver is doing the same thing it always was, sending SCSI packets to the VHCI. The VHCI is selecting a path down which, a physical path down which to transport the packet, and cloning the SCSI packet for that specific path, sending it to the PHCI. The PHCI is actually completing the operation. An interrupt occurs, matched it with the SCSI packet to the PHCI. There's a field in the SCSI packet called packet complete, which is kind of an extension of the interrupt back to the target driver, the SD target driver, or the VHCI that cloned. In the case of MPxIO, the callback is actually back to more VHCI code that then finds the SCSI packet initially sent by the target driver and then calls packet complete on that, getting back into the SD interroutine to look at the status of the actual packet. One of the things that we will be doing in this area for FMA purposes is actually recording which physical path a given packet actually went on. You know, right now that information is kind of like totally lost. So, relative to FMA events and so forth generated by a target driver, we're saying I got a check condition or I got a ECC error during transport or something, but we're not saying, we may have physically oriented events occur relative to transport that are not at all visible in any e-reports generated by the driver, because all the driver knows about is the virtual path. It has no idea which physical path actually incurred the problem. Data structures. I'm going to show you a picture in the ARC material, and I think right now I'm not going to go through this stuff. Okay, sorry. I'm sure that do I see any smiles? There are quite a few pages that Ramaswamy had relative to this, and what I'd rather do instead is go to the base level ARC directory for the initial MPxIO project. And there's sort of two things of interest there. So all this stuff is available. What did I do? Okay. SAC.eng is the machine that archives all of the ARC cases that occur. And actually a lot of those are now reflected out to Open Solaris too, so that you can actually see quite a bit of this material off of opensolaris.org. I'm not sure if this case actually qualifies. There's two things kind of I wanted to point you at in this directory. There's a related cases file, okay, which is sort of so this was a base, the first PSARC case to introduce MPxIO. Primary author of a lot of this was John Danielson. And there have been a lot of cases that have been follow-ons or related to this. And so I try to actually keep this related cases file up to date as new, just as a point of reference for people who are, trying to figure out MPxIO and get their brains around, what the evolution has been. And so all of these are actually links to other cases. Well, they should be. Oh, I didn't. That's a good point. I need to put .sun.com for people who don't fully qualify. You notice how the primary URL has .sun.com on the end? These links don't, so they're not actually resolving from this browser. And Open Solaris-wise, going forward, for any cases that are open, we really ought to have an equivalent file that refers to the ARC material in Open Solaris. Anyway, that's a good resource that kind of covers most MPxIO related things. And this is kind of my MPxIO cheat sheet. So instead of trying to go through all the data structures, I'd like to just kind of go through this diagram a little bit because it shows how everything's linked up. And let's see how this goes. So let's start with this picture up here. This represents sort of a view of two drives, okay, one of which has 2 ports into the device identity. The other one has 3 ports into the device identity, okay. We have 2 PHCIs, and then we have the virtual HBA. So we can see the port identities, target port identities from each PHCI differently, and those are going to be populated in the namespace. From the VHCI, we only see identity type information based on the LUN identity. This is taking this physical view, this is abstracting it out into the dev info tree. These are HBA dev info nodes. These are under MPxIO. With MPxIO disabled, these would be dev info nodes for SD off of a PHCI. With MPxIO enabled, these are actually path info nodes instead. Okay. And this green one actually represents a single PHCI that has multiple target ports to the same LUN on the same HBA. In regard to the data structures, we have, this is organized with so follow these squares into the tree, okay, follow them also down into the data structures. So a green square is this VHCI, is this dev info node, okay? And if you have a dev info node, which is a VHCI, it's actually linked on a list of all VHCIs. And the way that when MPxIO was first delivered, instead of actually extending the dev info node and changing its size, we came up with, to reduce risk, we have addendums that are basically part of the dev info node, but they're not contiguous in the data structure. So they're pointed to by the dev info node. So this is the type of a VHCI extension to a dev info node. Okay, and likewise, this is the extension for a PHCI. So the dev info node itself will identify this as in flags as being a PHCI, in which case this field is known to be the pointer to the extension. Same over here. Flags inside the dev info node, which strictly speaking is just this, plus a bunch of other fields that aren't displayed, will use the same field, but this time linked to a VHCI. And then so PHCIs, VHCIs, further down here we have client nodes. So there's an awful lot of detail in these slides. The basic idea, though, to get is VHCI stuff, PHCIs, linkages going. Let me shift this down one more time. From the VHCI, linkages going, around to all PHCIs. From the VHCI, linkages going down to all the clients that you have. Then in the middle of the picture, with the red dots, are the path info nodes, and they are also linked into this matrix both from the client standpoint and from the PHCI standpoint. When you select a path, you're actually selecting, a specific path info node and transferring the SCSI packet to the PHCI that relative to that path info node's linkage. I don't think I really, again, we have extensions to the data structure. This time there's a separate field for the client extension. With MDB, : print is a good way to actually, see all these fields and follow linkages. In addition, there are some MDB type support for this. So, I'm really at this point for the data structure slides here. I'm going to spare you. Really, I think the high-level view of how things are linked and so forth is all that I could hope for you to come away with some understanding for. For here, we talked a bit about the state model. These are alloc is a way to get an initialized path info node. Online and offline are actually adjusting the states. We talked about how path info nodes are peers of dev info nodes, and just like dev info nodes, they have properties. They currently require separate interfaces in order to access those properties. And when we do get to actually have SCSI understand more about NDI and MDI, what will likely happen there is that we will have, SCSI prop versions of these relative to SCSI device structures and so forth, where the device structure may refer to a dev info node or it may refer to a path info node. So these interfaces will not ever go public, but I would expect an abstraction within SCSI someday to actually allow property access from an HBA driver to path info properties without violating interface definitions. I'm going to skip locking. Miscellaneous things. A lot of these actually have private fields within that allow either a VHCI or a PHCI to store its own private data. within the path info node or within the client. That's sort of like an optimization so that it has an extension mechanism for other parts of the architecture that can build on the existing data structures, kind of like the driver private stuff that you get within a normal device driver. Turning MPxIO on and off. We have a utility that makes this kind of easy if you're doing things relatively globally, which is STMS Boot. Enabling it it actually repairs VFS tab and the dump information in regard to changing the namespace from a MPxIO oriented addressing namespace to a VHCI device identity oriented namespace. In addition, we did talk momentarily about being able to enable or disable for specific devices or override within SCSI VHCI.conf in order to select a specific failover module or to indicate that you do not want a device which otherwise would actually be supported under MPxIO to be, you want it to show up under the PHCI instead. By using just the generic property mechanisms, whether it's a global property or a per port property within fp.conf or in the case of MPT in mpt.conf. Again, you turn on MPxIO, your names change. And while STMS Boot does a good job for things that are represented in VFS tab, for some database applications, that's not enough. And STMS Boot does have some options to list what the translations are as an aid for applications like that. That's the STMS Boot -L options. Tools, we do have PRTconf, where you can actually start at, a dev DSK CTD name and actually see all the paths, see some of the status information. We also have in MDB PRTconf, ::PRTconf, and that actually needs to be enhanced. And that's one of the things that occurred to me in looking over these slides. We're kind of out of sync with the utility PRTconf and the MDB dcommand PRTconf, in that it does not currently show path info nodes, and it really should. It would make it a lot easier to go to link things together in that complex data structure diagram that we were on a few slides back. We have various IO-stat operations which try to amalgamate device usage from different viewpoints, from either the target port or the actual controller, or relative to a specific LUN, to try to, in symmetric configurations, determine how your load balancing is working in particular. And Jan talked yesterday about MPath-ADM, which has a lot of options and is based on the SNIA MP-API, multipathing API standard, which the SCSI VHCI code implements a lot of the interfaces required for providing that MP-API information. So supported devices. In 8 and 9, initially the development was done for 9. NWS backported it to 8 and kind of had their own delivery vehicle versus as SFK, as part of the SFK. In 10, VHCI code went into ON, so it's in the same place now as the MDI code. So most of the core part of MPxIO is in ON, but the Leadville stack portion, in the case of Fiber Channel, is actually in the network storage consolidation. iSCSI initiator code is all in the network storage consolidation, and that was developed in Nevada and then backported to the iSCSI stuff to 10. MPT was also a recent Nevada addition and is just about to go back to 10, I believe. I think it'll be in update 5. I don't believe that the MPxIO MPT made update 4. So for x86, MPxIO is on by default. We tried to put it on by default for S10 and ran into some kind of unexpected difficulties, not related to the technology or anything, but related to customer use practices. We have lots of customers that set up Jumpstart installs with fixed CTD names. And while there are advantages of putting device identity into the public name, from the transparency of device path and path independence and so forth, there are disadvantages too, because each one is now unique. And so for any customer that had Jumpstart profiles for their Sunblade 2000 internal drives that used fixed CTD names for those, well, that worked out fine with prior to MPxIO, but with MPxIO enabled, each CTD name for each machine that they were trying to share a Jumpstart install profile for was different, and that difficulty was enough to actually force us to not enable it by default for Spark. You're capable of doing that type of thing with Jumpstart. It just was not customer practice, and we didn't really want to perturb the customer base in that way with the small amount of preparation we would have had. So it's off by default. Use STMS Boot -E on Spark to enable it. Debugging. So now debugging for MPxIO is pretty automatic. It used to be that there was a separate module for the MDB walkers and commands. Now they've been put into modules that match the names of the modules, so they auto-load. So there's a SCSI VHCI module, and the MDI macros are all part of the Gen Unix MDB set of D commands. If you want to cold start looking at that complicated data structure diagram, the easiest thing to do is to just type this D command. And as part of that, you'll actually see you can cut and paste additional. That shows you the clients of SCSI VHCI and gives you cut and paste to find path info nodes and from there PHCI nodes. We don't really, to my knowledge, have this support could be improved, and part of it would be like to do a : PRT conf, which actually understood path info nodes as a peer of dev info nodes. Changes in S10. We've already kind of talked about some of the major stuff with FFS. We talked about enable by default. Support for more devices. That's likely referring just to the compiled in tables in the VHCI failover modules. We do have MPxIO now on x86 by default for that. You can turn it off with STMS Boot -D. And we now have, thanks to Wayne, the TPGS support. And ALU is just a pre-standards approval name for TPGS. More changes that have occurred in 11, and almost all of these I think everything will go back except for this last one, and this last one is just, the RTI's filed, the check's in the mail. All of this stuff has gone back to update 4. So if you have update 4, you have all of those. The plugin architecture for failover ops, that's what we're doing in regard to the open source is a start in that direction, in that we now actually do have separate modules for the plugin, and a motivated user could actually now add their own plugin module. We're not ready to go public with the details of the interfaces and so forth, but the source will be on Open Solaris, and without too much work, you could, and some tweaks to scuzzyvhci.conf, you can now add a third party could actually add a failover, its own private failover ops. Load balancing algorithms, that's kind of something that got implemented a little bit incorrectly, and the path selection stuff in general. It went back into the MDI code, and which is generic, and the MDI code has no real reason to know about things like LBAs. Okay, that's what the MDI code should do, is report a set of paths which are functional, and then the specific VHCI should select from a set of functional paths relative to an additional level of path selection based on load balancing, or which may include logical block types information. So we have some work to do there. Eventually get the failover stuff into public-based interfaces. We have the SCSA public interfaces, which is what I was referring to, really having SCSA updated to support dynamic configuration of both PHCI children and VHCI children. We've made some progress on FMA error reporting in regard to the Thumper platform, in regard to, we now have a generic topology, but there's a lot more work to do there. I don't really have any additional comments on the other items. Friendly names is something that we've needed for a long time. One thing that, in talking about the file systems, the dev file system is actually now a file system in Nevada. There's no intent to backport that, but in the same way /devices is dynamic, you can actually make /dev dynamic and avoid reconfiguration reboots and do more namespace that's not specifically path-oriented. So there's some work to do there. And the other things you can just read. Now we're to reference documents. I would recommend going to the primary case here, and then just looking at the reference, the references.html file there to find all the other MPxIO related cases. We also have dhs.central has a project page for MPxIO. There are some presentations and so forth about MPxIO on that site. Yes?
One comment I was going to make on the future work on that second of the 2 slides was relative to tape.
Okay.
In that work is ongoing right now to enhance both the SCSI VHCI driver and the ST driver to allow or enable multipathing to tape. So that is something that's ongoing.
We're taking a bit different tack to that too. Instead of relying on the fiber channel protocol for reliable error recovery, we expect to have that error recovery part of the ST driver. So we won't have, there's been, from the beginning, the FC2 layer has actually had some error recovery capabilities that were optional. And different vendor, a lot of incompatibilities among vendors in regard to FC2 error recovery. So instead, we actually expect to drive error recovery using logical block addressing modes on the tape drive and drive it from the target driver instead of transport dependencies, which would not work for like iSCSI tape or stuff like that. Yeah, so DHS.Central has some more presentations and so forth. I imagine this one will end up on there. And that's it.